Hello, everyone. My name is Isaac Tupac. I work in the Hicamarca Radio Observatory, and today I'm going to talk about one of the projects that we are developing, and is known the initial design of a GNU radio interface for a new version of the Hicamarca acquisition radar system, also known as JARS 2.0. Well, a bit about Hicamarca Radio Observatory. Hicamarca Radio Observatory is located in Lima, Peru. It studies the equatorial ionosphere. Uh, it is important and because its specific location uh, gives us the possibility to point directly and vertically to the equatorial ionosphere. We have one of the most powerful incoherent scattering radar that help us to make the determinant experiment. Well, we can see here in the photo the main antenna of the Hicamarca Radio Observatory. It is composed of 18,432 dipoles, linear dipoles, and it works in a frequency of 49.92 megahertz. Well, here is the Hicamarca acquisition radar system, the new Hicamarca acquisition radar system. We have four special boards. Here we have the clock board. Here we have the acquisition board. Here we have the bus board, and here we have the control board, or also known as SP601 development board. Now, how do they interact? Well, first we have the radar controller. This radar controller send or originate the clock master of 60 megahertz and send it to the clock board or the clock distribution board. This clock distribution board will send or will distribute the 60 megahertz signal clock to the other parts of the system acquisition radar. Also, we have two important signals, the synchronous signal and the window signal, that have the purpose of separate or indicate the amount of samples that we will save. I'm going to talk about this a bit later. Well, how did it work? First, we send the commands of configurations to the control board. This control board have two principal structures. The control or an FPGA Spartan 6 that have the function of implement an IP core that help us to obtain the data in gigabits per second, of the rate of gigabits per second. And this Ethernet, physical Ethernet, make us to send that rate of data through the gigabit Ethernet. Well, next, the commands are sent to the bus board. In the bus board, we have two FPGA Spartan 6. This FPGA is known as programming, and this FPGA is known as transfer. What makes this FPGA? It will send the program signal and the enable signal to the acquisition board, to each acquisition board. Then, after the acquisition board received the modulated signal, it will send a ready signal to the FPGA 6. This FPGA will return and enables signal to the acquisition board, to each acquisition board, in turns, because we have only one bus of data that they share. So each acquisition board will receive one enabled signal in the time. Next, the acquired data or the sample data obtained will pass to the data bus. First, it will go to the transfer FPGA, then will go to the control board, then will go to the port of Ethernet, and will pass to the gigabit Ethernet to go to the PC acquisition, and the data will save here. Now we can see here the implementation of the YARS 2.0. We have here the bus board. We have here the acquisition board. We have an LVDS interface between the control board and the bus board. We have here the clock board or the clock distribution board, and in yellow we have the Ethernet, gigabit Ethernet that go to the PC of acquisition. Now I want to focus in the acquisition board. So first we receive the modulated signal in one channel in acquisition board. Imagine, well, the acquisition board actually have two channels. So we are implementing, or we are showing here only one signal, or one channel. Well, first we pass to the ADC AD6645. This ADC digitalize the signal modulated and give us 14 bits in a resolution of 14 bits. Then we'll pass to two registers, and they will give us each sample data in 16 bits of resolutions. Then it will pass to DSPs of digital signal processor that demodulated the incoming signal in quadrature. When the signal has already demodulated, this DCP will send us two signals, IQ and DV signal. These two signals will originate a ready signal with the help of this block, the data enabling. This ready signal will go to the FPGA Spartan 6 and originate an enable signal, a signal of enable. Also, these two signals will originate two clock signals, and these two clock signals will serve or will have the functions to output in the two registers, in the two final registers, the modulated sample signals. So after the signals come to this DSP, goes demodulated the in quadrature part and the in phase part and in quadrature part to the registers, and they wait until the enable signal until they receive the enable signal and go to the bus of data to go to the PC of acquisition. We also have a specific power block, and they have the function of turn on each of the acquisition boards in turns. So how does How do these signals work? Well, we have the clock signal of 60 megahertz, and we have the two signals that are originated after the modulated, the DSP. So when the IQ signal and the DV signals are originated, the data demodulated are here in phase and quadrature signal or quadrature data. But this is for the acquisition board number one. This acquisition system have four acquisition boards. In each board we have two channels. So we have the data, the demodulated data in the first acquisition board. We have the second second demodulated data in the sub-acquisition board, and we have the fourth acquisition data in the fourth acquisition board. How do they go to the path of data? Well, we need the signal ready and the signal unenabled. When the data come or is waiting in the first acquisition board, it will pass to the path of data if the enabled signal is originated. Then we have to wait to then the second acquisition board have to wait to the second enable signal to go to the data path. And also we have to go, if we see here, the enable signal are different in time. They are next to each other in time. So that help us to specify which data go first. For example, this go first, so this data will go first, this data will go second, this data will be the last data to go to the PC of acquisition. Well, we can see here the acquisition board, which all its part implemented, and we have here the two channels. So, how do we obtain and save the data? Well, we first send the modulated signal, RF signal, to the ionosphere. Then we receive an echo, but this echo will not with noise, so it's not sinusoidal at all. Now, here we have this echo in the microvolts and time. So at the moment that we sampled the data, we will represent it as a point. One point will be one sample of this signal, and each point of sample will be one height of where we found or we obtained that data. So H0 will be the height of reference, and each sample will be different for a resolution named DH. All that data, all the space, we can say all the space where we can find the data, we will know as a window. Each data is specified, well, the height of each data, of each sample data is specified as with this formula. We use the speed of light, the time until the echo is received, and divide it by 2 because it's send and receive. So If we want to see it more specifically, here we have one IPP, two IPP, and for this experiment, we could say that we have 25 IPPs or interpulse period. In each IPP, we'll send the data, the signal, the RFF modulated signal to the ionosphere. Then we'll receive the echo in a Windows. Each sample data is represented, as I said, as a point, as a red point. So we have one sample, the signal, we have the second sample, and the last sample. Each sample is different but by a resolution, and the total of samples that we obtain in one IPP is known as one profile of samples. So for the second IPP, we have the second profile. For the 55 IPP, we have the 55 profile. We can specify them with a metadata known profile per block, and we can specify the amount of IPP with a metadata or attribute name number of IPP and dx. This will be the attribute. So how do we know, or how the system acquisition knows when start and when begins and where start and when finish? When the IPP required for the experiment, we will need a signal known synchronous signal that come from the radar controller. Now, how do we save these profiles? Now imagine that we have one sample data saved in memory of this profile. Now we have the second sample saved here, and we have the last sample of this profile saved here. But we don't have, as I said, one channel or one input in the acquisition board. We have two inputs in each acquisition board, and we have four acquisition boards. So we have 8 channels of input. So if we look in the second channel, it will also receive data. So we have another sample we save in memory that we will know channel loss that represents the data acquired, the data obtained for the input loss, for the input 2 in this profile. As we don't have only one channel and one channel input, as I said, we have 8. We will receive the last sample 8, the last sample obtained for this profile